Students, welcome back to another episode of distance learning class of grade 9 science, and we are in the continuation of the chapter simple machine. In our last class we discussed on what simple machine is and some parameters related to simple machine which we encounter while discussing about different types of simple machines. In last class we discussed on what load and effort in a simple machine are. We discussed on what load distance and effort distance are in a simple machine. Similarly, we discussed on input work and output work. Similarly, we tried to understand what mechanical advantage is in a simple machine and what velocity ratio is in a simple machine. So these were the parameters we discussed on in our last class, and in today's class we will furthermore, so the next parameter that we need to understand in a simple machine is efficiency. Efficiency. Now, what efficiency is? It is symbolized by a Greek letter eta, efficiency. Now, what efficiency is? Now, we apply some effort to a machine and finally the machine does some work for us. So, while applying some effort to a machine, we do some work to the machine and finally the machine does some work for us. But the work that we do to a machine and the work that a machine does for us, they are never equal. Practically, they can never be equal. The work that a machine does for us, that's output work, and the work that we do to a machine, that is input work, they are never equal. What I mean to say is, the output work, the work that a machine does for us, is always smaller than the work that we do to a machine or than the input work. So, efficiency. Efficiency is out of the input work, how much output work we get. How much output we get, that is the efficiency, and it is generally calculated in percentage. So, mathematically, efficiency of a machine is ratio of output work to input work. Efficiency is the ratio of output work to input work, and mathematically we obtain this in percentage. So, output work to input work times 100%. So, this is the efficiency of a machine. Here we are dealing with simple machine, so let's say this is the efficiency of a simple machine. And in no machine, these two are equal. In no machine, these two means output work and input work. In no machine, these two parameters are equal. Now, what's the reason? What's the reason? No machine is frictionless. No machine is frictionless. Suppose if we think a machine is ideal, means if we think machine is completely frictionless, then suppose to overcome a load of 100 Newton, suppose we apply just 25 Newton of effort. To overcome load of 100 Newton, we need to apply 25 Newton of effort. This much effort is sufficient to overcome this much load. Suppose and the machine is 100% frictionless, right? But practically, no machine is frictionless. So what we need to do is, we need to apply some additional amount of effort there. So with X Newton here, some additional amount. And this is why do we need to apply some additional amount of effort here? Because of the friction acting in different movable parts of the machine. If we take an example of a lever, a load is here, we apply some effort here. So to make it move about this point, definitely there occurs a friction between this lever and the point of the fulcrum here, at this point. Friction is acting there, or friction acts there. So due to this friction, some additional effort is to be applied at this point, right? So due to this reason, our output always becomes lesser than input. So efficiency is never 100%. If we say efficiency of a machine is 100%, that's ideal one. Practical, that is not possible. Just theoretically, we can assume a machine to be 100% efficient, but practically, that is never possible. So efficiency, it is the ratio of output work to input work, and mathematically we calculate it in percentage. So output work to input work times 100%. Now let's relate efficiency to mechanical advantage and velocity. Relation of efficiency with mechanical advantage and velocity ratio of machine. So what is output work? Output work is load times load distance. What is input work? Effort times effort distance. So 100% as it is. So can we write this way? Load upon effort, and effort distance upon load distance. So you understand this much simplification. So load and effort. Load to effort means what? It is mechanical advantage, and effort distance to load distance, it is velocity ratio times 100%. So efficiency, mechanical advantage, and velocity ratio, these are related this way. So efficiency is equal to mechanical advantage divided by velocity ratio times 100%. So this is the relation between efficiency, mechanical advantage, and velocity ratio of a machine. So these are the parameters which we need to understand before discussing different types of simple machine. Now let's go to the types of simple machine. So there are 6 different types of simple machines. The simple devices that we get to see in our house or in and around our house are this one: lever, pulley, wheel and axle, inclined plane, wedge, and screw. So these are 6 different types of simple machines that we get to see in our daily life. So all kinds of simple devices, or any kind of simple device that we use in our daily life, can be categorized under these 6 different types. So if you think of any simple device, that definitely comes in any one of the types mentioned here. So first one is lever. Now what the lever is? What is it? Lever, it is a long rigid bar. Rigid bar. It's a rigid bar. It is not flexible, it is rigid. It should be rigid. So lever is a long rigid bar, stick-like structure, which is capable of rotating about a fixed point. This is a fixed point, and this rigid bar is capable of rotating. Suppose this is a fixed point, and it is capable of rotating about this fixed point. So this is a rigid bar, and this is a fixed point, and it is capable of rotating about this fixed point. And this fixed point is called pivot or fulcrum. Fulcrum or pivot. And at one end of the rigid bar, load is there, and next end effort is applied. So a lever is a rigid bar capable of rotating about a fixed point called fulcrum. This fixed point is called fulcrum, and this rigid bar is capable of rotating about this fixed point, about this fulcrum. And at one end of this rigid bar, load lies, and at the other end, effort is applied. So this is lever. So lever is a rigid bar capable of rotating about a fixed point called fulcrum. Now, this lever, it is of three types. Lever is of three types: first class, second class, and third class. You can have a glance on the screen of the lever: first class, second class, and third class lever. First class lever. Second class lever. So from the picture also you might have collected some idea. Third class lever. What differences do you see in the three different types of lever? First class lever. Fulcrum is in between load and effort. Effort, load. In second class, load is in between fulcrum and effort. And in third class, effort is in between load and fulcrum. So see, first class lever. Fulcrum lies in between load and effort. In second class lever, load lies in between fulcrum and effort. In third class lever, effort lies in between fulcrum and load. So FLE, you can make a formula to memorize: fulcrum, load, effort. Fulcrum in between first class, load in between second class, effort in between third class. So these are three different types of lever. So all the levers, all the examples of levers can be categorized in these three different types. Now let's find out some examples. Okay. So which devices, or what kind of devices do we use in our regular basis? Scissors, yes. We use this in our regular basis. What else? Knife also can be categorized in lever, in a type of lever. Knife. What else? Spoon, shovel, a crowbar, very common example, crowbar, tong, forceps, pliers. These are some examples. bottle opener, lemon squeezer. Now see, let's classify these examples. These are some examples of so many levers. Scissors. So this is the point. See, there are two levers here. So scissors. Now our load lies here. This is the fulcrum. We apply effort here. This way and this way. We apply effort here. So load lies here. Load, fulcrum, effort. So this is which class? First class. Knife. So this is knife, suppose. So how do we use knife? So while using knife, while chopping anything, or suppose vegetables in the kitchen, we use knife this way. So load lies here, right? So we are pressing here, effort here, and if this lever or this particular device moves about this point, so this is fulcrum, this point is fulcrum, this point is fulcrum, load, effort. So effort is in between load and fulcrum. So which class is it? Third class. So spoon. While taking our meal, how do we use spoon? Suppose this is the pan and the spoon, and it holds our meal, our food. So load is here. So we apply our effort here, and this is fulcrum. So which class is it? Third class. So well in the same manner. Crowbar. Load. Suppose we need to turn this load. So fulcrum, load, effort. So which class is it? This is which class? First class lever. Tongue. Forceps, sugar tongue, fire tongue. Right? So there are different types of tongues. So how do we use the tongue? While using the tongue, see, we apply effort here, load lies here, effort, load, and fulcrum. So which class is it? Third class. Effort lies in between load and fulcrum, so this is third class lever. Pliers, that is similar to scissors. Bottle opener, lemon squeezer. So in lemon squeezer, load lies here. This is fulcrum, this is load, and we apply effort here. We press it from here, from this point. This is the lemon, our load, and this is the fulcrum. So which class is it? Load here, it is lying between fulcrum and effort. So it is second class lever. So please, dear students, you try to find many examples that you get to see, different devices that you get to see in your house, in and around your house. There are much more devices that you are using at your home. If you just go into your kitchen, you can find more than this. If you just look in and around your house, you can find more than this. So first find all kinds of devices there, and then try to find out which class of lever they are. So let's move further. Now let's discuss on the different parameters in lever. Load, this is fulcrum, effort, this is first class lever. This is fulcrum, load, effort. This is second class lever. Fulcrum, effort, and load. This is third class lever. This is first class, this is second class, this is third class lever. See? So when fulcrum lies between load and effort, this is first class. When load lies between fulcrum and effort, it is second class lever. And if effort is lying between fulcrum and load, it's third class lever. Now, what is mechanical advantage in first class, second class, and third class lever? Mechanical advantage. It is load to effort. In first class lever, fulcrum can be exactly at the middle. Fulcrum can be exactly at the middle. So if so, load and effort, they are equal. If it is exactly at the middle, load and effort are equal. If you assume this particular device to be frictionless, if you assume this to be an ideal device, then when fulcrum is lying, if it is lying exactly in the middle, load and effort are equal. So if these two are equal, it is equal to 1. And if fulcrum shifts slightly towards load, in this case, effort that we apply is always lesser than the load. If so, it is greater than 1. And if we shift this fulcrum towards effort, then to overcome the same load, we need to apply effort more than the load. If so, mechanical advantage is less than 1. Now see the condition. In first class lever, this fulcrum, it can be exactly at the middle, it can be slightly towards the load, or it can be towards the effort. So when it is exactly in the middle, it is equal to 1. When fulcrum is towards the load, it is greater than 1. When fulcrum is towards effort, it is less than 1. Now why so? Why so? If it is exactly at the middle, then effort distance, if it is exactly at the middle, then effort distance means this distance and this distance. Effort distance and load distance, they are equal. If effort distance and load distances are equal, if these two distances are equal, and if you are assuming this device to be an ideal device, 100% efficient device, just suppose, we don't know how much friction is acting here or acts here. So let's suppose it is an ideal machine, it is 100% efficient machine. If so, and if this fulcrum is at the middle, in that case, effort distance and load distance, these two are equal. If so, effort applied is always equal to load overcome. So in that case, this becomes equal to 1. But if we shift this fulcrum towards load, what happens? For a small load distance, the effort distance becomes larger. So when effort distance is larger or longer than load distance, in that case, effort applied or effort required is always smaller than the load overcome or the resistance overcome. In that case, see, if effort applied is smaller than the load overcome, then this fraction becomes greater than 1. Similarly, if this fulcrum lies towards effort, what happens? See, in this case, the effort distance is smaller than load distance. So when our effort distance is smaller than the load distance, then effort required is always much more greater than the load overcome. If so, this fraction or mechanical advantage, it is always less than 1, right? So in case of first class lever, the mechanical advantage can be equal to 1, can be greater than 1, or can be less than 1. Now let's go to second class lever. In second class lever, see, load always lies between fulcrum and effort. So wherever the load lies, here, 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 the effort distance, this is the effort distance, so load is here, so this is the load distance. So effort distance is always greater than the load distance. Effort distance is always greater than load distance. So when effort distance is greater than load distance, effort required is always smaller than the load overcome. So in case of second class lever, MA is always greater than 1. In case of second class lever, MA is always greater than 1. It is never smaller or equal to 1. So wherever the load be, here, 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 or suppose it is here, it is still load distance is still smaller than effort distance. Now in case of third class lever, now see, suppose we apply effort at this point, so this is the distance traveled by effort and this is the load distance. So here, load distance is always greater than effort distance, or effort distance is always smaller than the load distance. So effort required is always more than the load overcome. So we need to apply effort always more than the load. So in case of third class lever, mechanical advantage is always less than 1. But still we use third class lever. Why? See, using shovel is third class lever, and using shovel, while using shovel, the effort that we apply in shovel, it is always more than the load that we lift or throw away. But still we use it. Why? Simple machines, they have different advantages to us. So we don't use simple machines only to magnify the effort that we apply. Sometimes we use simple machines to make our work easier, even by applying effort more than the load. Suppose if we need to throw a heap of sand from one place to another place, and with our bare hand or palm, how long it would take to throw from here to some other point. But using shovel, we can do it in lesser time. See, it has made our work, or it makes our work quicker. No matter we need to apply effort more than the load. So that's why we use third class lever in our daily life, even though it doesn't magnify the effort applied. Dear students, so I want to conclude today's class here. This was for today. So please repeat all these things at home. Try to revise, try to understand something yourselves also. So in next class, we will come with some other topics of the chapter. So till then, have a good time. Thank you. Bye-bye.